So we are just starting Chapter 4 in this book right here, Causal, Inference, and Statistics. And this is the final chapter, and it's a challenging but interesting chapter, and kind of quite a bit of fun, actually. So I'm going to make two videos back to back here, and I suggest that you watch them back to back. But Chapter 4 deals with counterfactuals, okay? And counterfactuals are a little bit of a different beast than what has come before. And I find that the way that Pearl talks about these is very much like somebody who is very expert in them and has difficulty trimming the fat and getting, being able to express this to somebody who's not familiar with it. And so before we get into the questions, question 4.31 being the first one, I want to offer just a little bit of a primer, just a little bit of runway that we can use to gain some momentum going into the first question. So in this video, I'll talk about, I'll work through a primer, and then in the next video, we'll start with question 4.31. And so like I said, I suggest you watch these in rapid succession because I'm going to borrow some elements from question 4.3.1 for this counterfactual. Okay, so like I said, the reason I want to make this primer, and I haven't done this for for this book at all, is that when I first learned about counterfactuals from this book, I found it really confusing. I'm not really sure why. Like I said, I think part of it is because Pearl is just so expert in this that that it's a little bit hard for him to have some empathy for people that are just coming to this new. And so I find that it takes all sorts of twists and turns, but I think that the explanation can be made much simpler. So, so why is this chapter a little bit of a deviation in what has come before it? Well, previously we've been learning, the tools that we've learned are estimating causal effects as averages across many cases. Okay, right? So you think about anything that we've done, like if you take this little DAG down here, we might try to find the total effect of x on y or something by regressing y on x, and so on. And then and alternatively, we might look for if this was a more complicated DAG, we might look for backdoors and close those backdoors and da 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 da. Okay, but counterfactuals are doing something slightly different. And that is they are estimating outcomes of individual cases. Okay, so just compare these. So causal effects, so maybe like trying to estimate A here across, as averages across many cases. And here we're estimating outcomes, so for instance, Y, in individual cases. So not everybody, but just a few cases. Okay, some particular cases. Okay, now that's the main gist of it. Now, but you can use, you can use these tools. You can get creative and be more flexible with it. But I think that's a good initial way to initially conceptualize these things. All right. So the function of the counterfactual is represented in its notation here. Okay. So here's the notation that gets used, and so we should read this as something like this. Okay. The expected value of y, if I set the variable x to some value, hypothetical value x that I'm calling x prime here, in cases where z equals z. Okay, that's it. So let me say that again. So this notation says, what is the expected value of y if I set x equal to x prime in cases where z equals z? Okay, so that's it. So I need to say a little bit about this idea of cases where z equals z. All right. So if we think about each of these cases as being a single person, just as a way to imagine this in a way, okay? Each of the measured variables, so say x, y, z, all right. Well, whatever some person's value for x is, there's going to be a lot of things about that person that that give them that particular value, okay? And all of those unmeasured things that percolate to give them a value of whatever their x value is, all of those things get represented in u, u1 in this case, and for z it'd be u2, and for y it would be u3, although that's not shown here. Okay. And so when we are saying, in cases where, say, z equals z, right, we are saying for individuals for whom z equals z. So individuals for whom z equals z is going to select certain values of u1 and u2. Okay? So that's the idea here about narrowing our focus to only cases where z equals z. And so we might also call this something like the z-specific effect of, you know, changing x to whatever, da 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 da. Okay, and z-specific effects are something that we'll learn about later in the chapter. Okay, but you can already see how, you know, we could apply that right now, right? The z, you know, the z-specific effect of, you know, changing x or whatever, because we're only looking at cases where z equals little z. Okay, so just to explore a little bit more, we're going to use this DAG, which is the DAG that gets used in question 4.3.1. Okay, and importantly here, these u variables are unobserved. Okay, often you see a circle around the unobserved variables, but this book doesn't tend to do that. And each of those, they're independent of one another, and they're both normally distributed, you know, with mean 0 and variance 1. Okay. So we're going to start with an easy problem. So we're not going to start with, you know, what we looked at so far, this one. Okay. We're going to look at this one, the expected value of y when we set x equal to x prime in cases where x equals x. Okay. Now, so what we're going to do, we're going to find cases where x equals little x, and then we're going to set the value instead of little x to x prime. That's you know, how we can conceptualize doing what we're doing here. So the first thing that we want to do is to identify individuals for whom x equals little x. Okay, well, if we look at the DAG here, that's trivially easy, right? X equals u1, u1 equals x. Okay, so it is just, so if we are looking, you know, if we're trying to find individuals for whom big X equals little x, we just need to find, you know, it is just the individuals for whom u1 equals little x, and that's it. Okay. And so then once we do that, we can just set those, you know, those values, right? For those individuals, we can set x to x prime, and then just carry forward the DAG. Okay. So what does y equals, or what does y equal? Well, y equals z times b. Well, what does z equal? It equals x times a. Okay, so here we have this. Okay, and so if we set x to x prime, well, now we have a value of z for which x equals x prime. So we've calculated a new z value times b, and so that means that y is this z value, which is x prime times a times b. Okay, and that will give us the outcome for individuals in whom big X equals little x when we set x equal to x prime. Okay, so we can simulate this, and in fact, we'll do a lot of simulations here. So I just have a bunch of data points, right? And I have u1, right? And x, and u2, and z, and u3, and y. And so if you walk through this code, even if you don't know how to code, but it should be pretty clear what's happening here. I'm just putting this DAG into code, right? So I have u1. It's a normal variable with, so that's this, okay. And if I don't put anything else after that, I just have, you know, in data points with mean 0, and it defaults to mean 0 and variance 1. And now if I have x, well, what is x? Well, x is just u1, and I'm rounding it here. There's some chicanery that's taking place with all of this rounding, and there's a reason for it, and we'll see why here in a little bit. It's just a computation thing, just for the purpose of simulating. Okay, and now I have a, and a is its own value. It's not dependent on anything, and so I'm just going to choose a value for it. I'm going to choose 2. And now I have u2, right? And I have z. Well, what is z? Well, it's a times x plus u2, right? So I have that. And then I need to assign a value for 3, right? So I'm just making that up just to make the simulation run. And then I have u3, which is, of course, b times z plus u3. Okay? So we have the simulation, so we run it, and so now the computer knows I have all of these data points. And so now we can run this DAG forward and test to make sure that y equals what we think it equals. Okay, so we can do this directly. So I'm going to set x prime equal to 2. Okay, so now my new zx value, in fact, I'm going to call it this just to keep the notation consistent with what I do later. Right? It's the x prime value times a that gives me the new zx. Okay. Now, so one way that we could get at this is we could look at what's in our data, and so the way we could do this, we could say, well, what is the value of y in cases where x equals x prime? Okay. All right. So we do that. Okay. And then we could, so now when x equals x prime, well then z equals zx, so we could also check to see that in case, what is y when z equals zx, and those two values should be the same. Or we can just recreate the DAG, right? X prime times a times b, okay? Or that is also equal to zx times b, okay? And so they should all come up with the same value, and they do, okay? Now we could also run some regressions to make sure that this all follows, right? So so now instead of either just filtering through data where x equals x prime, okay, or recreating the DAG, now we're going to use linear regression to to estimate from our data and see if we get the same answers. So we're going to estimate, the values, the parameter values, and then build the DAG, basically trying to recreate up here. Okay, simulate again. Okay, so first we need so we have two simulations here. One where we regress y on x prime. Okay, and then we're just going to take beta, the beta from that times x prime. Okay, and that should give us the expected value for y in cases where sorry, sometimes it's hard to talk through these things. So we're going to have two simulations here. One where we're just regressing y on x, 4 values of y and x, where x equals x prime. Okay, and the other one we're going to do it piecemeal. We're going to regress in separate regressions z on x, right, to map onto our guy here, to our DAG, right? Z is informed by x, and then in the second regression we'll do y regressed on z. Okay, and then we will so from the first regression of regressing z on x, we'll get an estimate for z of x. Okay, and then once we have an estimate for z of x, we will use the parameter for the next regression to multiply by our estimate for z of x and get an answer. Okay. Well, I've already ran this, but again we get 12. Okay. So anyway, so that's how. So we went from defining a counterfactual, okay, and then found 3 different ways to test or estimate, the implied value of that counterfactual. Okay. Now this one was actually, like I said, trivially easy because we were just looking for individuals for whom x equals x. And so if it's not clear why that is trivially easy, okay, well, let's consider the more difficult scenario, which is the one that we will answer in the next video for question 4.3.1. What about where z equals little z? Okay, so if we go up to the DAG here, okay, well, when we were looking for when x equals little x, all we had to do was to find the individuals for whom big X equals little x was those for whom u1 equaled little u1 or little x. Okay, because that's the only thing that was informing the value of x. But now if we go to z, now there's two things informing the potential value of z. Okay? There is u2 and there's x. And now x is just u1, right? So in other words, for any particular value of little z, we have an equation that looks like this. Okay? Or this, right? ax or au1, same equation. Okay? And so we have one equation with two unknowns. Okay? And so there's many solutions to this equation, right? We nudge u1 up a little bit and nudge u2 down a little bit, and that's a solution, right? So, and if we have a solution, we just nudge one up and one down, and we continue to find more and more solutions, okay? And so the set of all of these solutions are described by a probability distribution, a joint probability distribution of u1 and u2 given z. If you need a little bit of expansion on that idea, I suggest you go back and look at question 1.5.1 and probably E, or the whole question. Okay, so it's this problem that we're talking about right here, right, that we will look at in the next video.